Well, good afternoon, everybody. I hope that you're all well. My name's Ed Morris, and I am technical manager for Altecnic. Today's Altecnic Tech Talk. We're gonna focus on some heat networks and heat interface units. Now, we're going to try and make this focus for more of a sort of engineering level and from the installers who have the potential to work on them. But we're going to cover off, what is a heat network, what is the association with HIUs, and then we're going to some different features and what to look out for when it comes to the actual HIUs themselves, should you come and have to do any work on themselves. So I hope you'll find it enjoyable, and we'll make a start. So first of all, we'll take a look at, what is a heat network. There's a lot of talk about it at the moment. Some people call them heat networks, some people call it district heating. So district heating is also known as a heat networks. It's a system of distributing heat generated in a centralized location through a system of insulated pipes for residential and commercial heating requirements, such as radiant heating and the heating of hot water. And what we can see here in these images is what we see as the pipe work that's laid under the ground. I remember talking to a contact of mine once, and he said, that sort of 40 or 50% of all roadworks that we see, across London and stuff at the moment are all actually people laying heat networks. So it is a large distribution of insulated pipes to the ground, which transport or carry hot water across. The picture that we see on the left-hand side is a typical sort of heat network plant. We have a centralised location that we work from, but typically, that's what we tend to see. So we have some kind of heat generation in one location with a series of insulated pipes, which take this heated water to its final location. So in turn, a heat interface or a HIU, and the heat generated by a central plant is taken by the HIU, and using the plate heat exchangers, this is transferred for use with either heating or hot water within the property. So essentially, that they are similar to what we see as a traditional boiler that hangs on the wall. But instead of taking the heat from a gas source, we're taking the heat from a primary network, and that primary network is what we call the heat or the district heating or the heat network. So just going to say, if we do have any questions today, there is a chat log on the side. If you type any questions in there, my colleague Helen, who's also on the call, she'll read those questions out at the end, so we can try and hopefully answer some of those questions for you. But pictorial-wise, this is our one of our K32 units. But what we see here on the right-hand side is a schematical view of a breakdown of a HIU. So we have sort of our plate heat exchangers, various valves, various components that sit within there, and then we have our connections out to the system. So we have some domestic hot water, and we also have our tertiary systems, whether that be underfloor heating or whether that be a radiant system as well. So quite flexible in the systems that we can install them into. We have that flexibility, especially with the units being electronic, which we'll touch on a little bit later on. But that is a basic schematical view. We have the primary flow, which is the hot water coming into the HIU. Then all that energy is used and then sent back out from the HIU back to the district heating to be reused. So we look at a typical gas network here, and the reason that we are using or that we're using this gas network is to show the differences between how we transport gas to a site and how we can transport the the water using district heating. So gas production, its very nature, is quite a cumbersome project to carry out. We have gas production, normally we have the drilling wells out at sea, which takes a hell of a lot of work to get these gas lines in place. We have to use gathering pipes. Those gathering pipes are there to transport the gas that's drilled up, and then we have to go to a processing plant. This processing plant adds purification, adds all the other bits and bobs of the chemicals that we need to get the gas working. And then we go to LPG, so we go liquidation, then we have to ship it, then we have to go regasification into storage. If we go the other way, we have to go for some storage systems, transmission pipelines, all the different gate valves, all the different systems that we have to use to make sure that we do that. So we have to work through that way. So I've just been told we might have a problem with the presentation, so bear with me for 2 seconds. I'm just going to try and share my screen again. Hopefully anyone can see that screen now. Is it working? Helen, can you see?
Yeah, I can see you, Ed. You just need to reshare your presentation, I think.
Okay, sorry, bear with me for 2 seconds. I do apologise. Can we see that now?
Great.
Yeah, can you see that?
Yep, it's there. I can see it.
Yeah. Okay, sorry about that, everybody. We'll go back again. We'll start again. If you have any questions, please put them into the chat log. So we talk about heat networks. We go through district heating, so it is a series of insulated pipeworks. Here we have some pictorial pictures of what they are. So we have the underfloor, the underground insulated pipes, many miles of insulated pipe, depending on where the heat generation is from, and that carries it to its final location and then back to the centralized zone. And the pitch that we see on the left-hand side is a typical, what is more traditional, a typical centralized plant. Back in the days when I was an installer on the tools, plant rooms were very sort of dark and dingy places to work. But we can sort of see now, as time has evolved, as things has moved on, we now have these very cleaner environments. A lot of it is electronically controlled, where before you'd need a team of people working on these networks or on these centralized plants. We can control a lot of this via remote, via computers, etc. So that's what we know as a heat network, or district heating. They are the two ways that it's referred to as. The heat interface unit, so that's basically where we transfer the heat from the heat network into the end product or into the end user's property. So we can start to use it for either central heating or for domestic hot water. Now that transition takes place via plate heat exchangers. That gives us hydraulic separation. So when we talk about the heat network or the district heating, we class that as a primary network. And to keep us hydraulically separated from there, we use plate heat exchangers. So the hot water from the district heating comes into the heat interface unit, to the HIU, enters the plate heat exchange. We then mix that within the plate heat exchanger with cold water, which then gives us the desired set temperature, whether that be for domestic hot water, whether it be for a radiant system, whether that be panel radiators, or whether that be underfloor heating systems. We've got all that control via the plate heat exchangers, and via the electronic units we have some stepper motors in there, which regulate the flow to make sure that we get that guaranteed set temperatures that we are working to. So that's the relationship between the HIU and the district heating. So the district heating is the deliverance of the hot water, and the HIU is where we use that energy for the distribution to the end user, or to the occupier of the property itself. So typical gas network, gas production, it's quite a cumbersome process that takes place. We have to drill for the gas, we have to go through all different kinds of processing plants, and also transportation. The gas network is huge. I know we're looking, we're decarbonisation, we're looking at sort of hydrogen networks and whether the gas networks can carry hydrogen to be able to use a hybrid fuel, etc. But if we focus on this as a single plant, the gas production is quite a cumbersome and quite a heavy carbon heavy way of doing things as well. Whether we go for LPG or whether we go for natural gas, there's certainly lots of different kinds of processes which have to take place for us to be able to deliver gas to an end user, and that goes through transportation, regasification for the storage of gas, transition pipe work, the mainline cells, all that sort of stuff is what it takes us now to deliver gas to what is essentially at the moment your gas-fired boiler, wherever you choose to do that heating. But that's the kind of network that we're looking at when it comes to gas. So we now look at what we class as a simplified heat network. Obviously, they are a lot more complex in reality, but if we try and look at it from a simplified perspective, what we have here is a centralized plant. So the building with the yellow roof and the blue and yellow chimneys, that is where our heat generation is taking place. And then what that's doing there is that is then sharing its heat between various different properties. So you can see we've got a little bit of industrial there, maybe a hospital, we've got some residential, some mixed occupational buildings, and some domestic dwellings as well. So what that's doing, that is generating its heat, we're generating its energy. And we do talk about heat as energy in this because that's what we use as energy. Generate it in a centralized location. We share it through a heat network, so through a distribution network of pipes. All that is being shared, and then it's been returned back to its centralized zone for then reheating to be reused. So we're working on essentially what is a big closed loop circuit, where we are constantly we're heating water, it's being used. As it cools down, we take it back to the centralized plant, and we then start to send it out again. So in a very simplified term, that's what we're looking at: centralized plant to use it, and then different areas of a town or a city to use that energy for the consumption of consumers. Energy centres, they've changed certainly very much over the years. Again, we spoke about traditional plant rooms, certainly, I say, refer back to when I was an engineer on the tools and I was a pipe fitter. A lot of it used to be in basements or underground. Plant rooms are always these horrible, dark and dingy places where nobody ever really wanted to go. They're always quite damp and not particularly nice places to work. But time has moved on, and especially when we start looking at energy centres or centralised heating zones for heat networks, times have changed. And the reason for that is that because there's going to be more and more of them, we want them to be more aesthetically pleasing. So we want these buildings to be able to fit in with the environment that they're being built in. So this one is the one in Gateshead. It's the district heating centre for Gateshead. The outside of it, again, you wouldn't necessarily know that was a plant room. It's quite a nice looking building, plenty of glass, plenty open, it's plenty airy. The big sort of clarifiers on the side, nicely coloured pink as well. So it kind of fits in with the environment that it's designed to be sitting in. It's not an eyesore, I think, is the important thing to look at. And again, the inside of it, when I was back on the tools, I were always, bits of metal pipe lying around, or screw machines, or different bits of machinery lying around. Whereas now they're very clean, they're very clinical, and that's due to the way that I think the sort of the focus has moved forward to make these clean and energy efficient running centres. Where before we could have had sort of maybe 10 or 15 different operatives having to go around there checking valves, checking pressures of expansion vessels, wherever else it may be, and checking pump pressures. A lot of this can be now be done remotely. So there's probably a small office with 1 or 2 operatives that's sitting there that can monitor this whole energy centre via its building control system to see what it's doing, adjusting the pump speeds, temperatures, etc. So as time does move on, we do end up in a different place when it comes to how things move. So that's sort of the evolution, and that's what they tend to look like. A lot of them, to actually gain planning permission, they have to sort of fit in with the environment. There's different ones around. There was one in Birmingham on the bottom of the Coventry Road, which is an incineration plant, but the building has to be aesthetically pleasing. At night time, it changes colour via LED lights, etc. But it just makes it not an eyesore on the environment, so it's better for everybody in and around the areas where these units are built. So how do energy centres work? So due to simultaneous production of heat and electricity in combined heat and power plants, or CHP plants, district heating is a very energy efficient. By implementing renewable energy sources and utilising waste heat generated by industry, the environmental gain by district heating is further evident. And this kind of energy utilisation is beneficial for both the environment and for the society in general. So there's an awful lot of talk now about low carbon and zero carbon and how we're going to start to reduce our emissions over time. And there's a big driver towards the way that we generate whether it be our heat or whether it be our power, or whether we do that simultaneously. So if you look, an old traditional system maybe run at say 45% efficiency. We can see the production plant there. We have these big power plants with these big cooling towers that are just pumping out the steam when they're cooling. You've got power lines, all these different sorts of ways to try and generate heat. Whereas now these CHP plants, they can be heated by biomass or any kind of renewable energy. Again, we spoke about waste transfer or waste for energy, where we have incineration plants. All these sorts of plants are generating heat. So instead of putting them out through say for instance, cooling towers, let's utilize that heat, let's utilize that energy, and let's start to use it for a benefit instead of just pumping back into the environment. I know there's a company in Scandinavia that produce acid. The natural production cycle of producing acid generates heat. They used to dissipate that heat throughout the system, and they use that as a saleable, a commodity item that they can sell into the network, because they generate enough heat then to be able to start running the heat network. So instead of wasting this energy like we used to do, via Quintas, we're going to start to collect this heat. We use big large clarifiers, so we can store large amounts of hot water which are needed for it. So we can see that new CHP can run up to 90% efficiency, so it's twice as efficient as the old traditional methods of how we do stuff as well. So it's always important to remember, we're trying to move towards this net zero carbon. And the way that we do that is by the way that we burn our fuels and the fuels that we use to burn. So it's very important that we do the right thing when it comes to those sorts of those sorts of environments. And there's going to be even more of a focus. We want to be carbon neutral by 2050. Sorry, we need to make sure that we focus on it. And some of the big heat generation plants now have got such advanced technologies in the way they deal with their emissions that's how we bring it down. We talk about a property with say 250 gas-fired boilers or different heat plants. We've still got the process of delivering gas to all those different areas, whereas now, we can control how the emissions come from one centralized plant and start to drive down the emissions, via that route. So it's quite important that we look at the technology moving forward. It is all about, it's all about evolution, not revolution, and we have to make sure that we remember that. So typically, compared to individual heating systems, district heating plants are better reducing emissions of hazardous compounds, since they have more advanced pollution control equipment, and through them more controlled conditions in generating heat. Furthermore, district heating is very convenient for consumers who hardly notice how their radiators and tap waters are heated on a daily basis. And I think that's another important thing to remember. A consumer of heating and hot water just wants to be able to have a good deliverance set temperature of hot water, and they want a steady temperature of heating. Now, they aren't necessarily too concerned about how that is delivered to them, as long as they're getting that, and a heat network can deliver that. If a heat network is set up correctly, and there are many out there that aren't, you're not going to notice any difference from as an end consumer as to how that is delivered. We can see here again, another typical sort of, this is a town, shall we say, and they've got various forms of energy efficiency here. So we have a power plant, which is obviously producing the heat network. We can see on the left hand side there the pipes that come from the power plant. That is then distributed around in insulated pipes. Now we've got to keep that energy within the pipes itself, and then we have different ways. So generally the place heat exchangers where we can exchange that, but they've also got some solar panels which generate some energy, and they've also got some wind farms. So all this together is going to start giving us far greater ways of control. And you can see there as well on this one, so we've got a data center. Data centers, by their very nature, where they operate using all the machinery, they generate a lot of heat. And so what this one is showing there, that heat is taken from the data center, converted via the power plant, by heating this, and then used as a heat network. So we're taking what would be before a waste energy, which is the heat side of things, and we're then going to start to to use that as a benefit, as opposed to a negative, and pump up into the skies. So it's important to remember that as well, that a heat network is sized correctly. Now, we work off what's called a diversity factor when it comes to a heat network itself. And what that diversity factor tries to calculate is a demand at any one time. So if we have a system that's got, say, for instance, 100 apartments, not at every one time where we're going to have 100 apartments that are going to be demanding heating, they're going to be demanding hot water. If we did have that, it's something is wrong. But if we design the system to counter for that, it's going to be massively oversized, because there's not that demand at any one time. So what we do is we work off what's called a diversity factor, and that's a calculation that works out at any one time we're going to have, say, for instance, a 17% demand on the system, and that's how we start to size the systems. Now, systems can be, when they're undersized or oversized, can generate problems in different ways. So generally, if we don't have enough, if they're undersized and we haven't got enough energy, that will have a knock-on effect on the end user, on the HIU, because we won't be generating enough energy. Again, if they're row size and we've got too much energy going through, that can then have a problem on the internal components of the HIU, and again have an impact on the end user. So that diversity factor is critical when people are sizing these systems, to make sure it's right. People move into only 2 or 3 people move into a development that's been designed for 200 people. Obviously, there's going to have an impact on that as well, because there isn't that huge demand on the system itself. So it's very important that our size correctly, using the right diversity factor. So some numbers around heat networks and where we are today as we sit here. So currently there's 14,000 plus heat networks in the UK, 91% of which are in England and 6% in Scotland, and the other couple of percent are sort of dotted around the rest. So we do have a large amount of heat networks already out there. It's going to be bigger, it's going to get larger. We work off the moment what is called a 3rd generation heat network. There are talks around 4th and 5th generation heat networks, using air source and ground source heat pumps, and then using some sort of boreholes as well to generate heat. But at the moment we're working off 3rd generation heat networks. And I think it's important that we can control 3rd generation before we start to move on to sort of 4th and 5th as well. So that's the important thing to remember. 492,000 connections in total. When we talk about connections, we talk about people that are connected into a heat network itself. So out of those 14,000 plus heat networks, we've got just short of 500,000 connections in total. 446,517 of those are domestic consumers. So we talk about homeowners. So a lot of these new build developments that we see in big cities run off heat networks, and there are actually towns now that are built around heat network itself, and there's a lot of conversion going on now. We certainly see through our sort of side of things of a lot of retrofit now, where they're taking away the old traditional ways of heating, and they're starting to install heat networks also, and district heating and HIUs into the systems itself. 33,000, so 32,000 commercial customers. So we talk about retail or similar. You know, they're also tapping into these networks themselves to make sure they're getting a bit of the pie. You know, getting reduced energy costs and all the good stuff that goes around that. So and 4,000 so retail customers. So these large shopping centres or anything to do with retail. You know, people are digging into these systems now to making sure they get the benefits. And quite an interesting one as well. You know, just shy of 1,500 universities as well. So, you know, the education sector, anywhere where we get these large buildings now, are starting to dig into these into the benefits of what heat networks can give them, and start to get some greater control over what they're doing, and some benefits from reducing the carbon as well. So you know, some interesting numbers around that, I think. And this is just a little flyer that was put out by the Association of Decentralized Energy, and this is just a little story really about the figures that were just around there. So keeping our homes warm costs nearly half of our total spend in energy. Heat networks are transforming heat, connecting individuals, families and whole communities to networks of pipes meeting their heating needs. The heat produced nearby, often recycling waste heat produced from generating electricity. So we talk there, you know, we talk about waste for energy, we're talking about anything that can start to generate heat. You know, we can start to use that to our benefit, as opposed to, you know, to waste it back into the environment itself. You can save yourself money, you know. They are low maintenance with no boiler to repair or nothing to replace. Low carbon, reducing carbon dioxide by 700,000 tonnes and a saving of 3,000 gigawatts of gas imports a year. That's the equivalent of 3.5 gas tankers. Imports and supply to 216,000 homes. 500,000 customers already on there. 14,000 heat networks connected to just shy of 500,000 homes. And this could grow to 8 million consumers by 2030 to meet the 17% of our heating needs. So creating potentially the estimated 81,000 jobs, up to £22 billion in capital investment. So it is something I think that there's a big focus on. You know, we hear a lot of stuff around the government and reducing carbon emissions and stuff, and you know, and heating is one of the ways we can do that by producing these centralised plants. So how does a HIU work? You know, we talk about the network, we talked about the relationship. Let's have a quick look now on how it works. So for the district heating network, the heat producing plant pumps heated supply water to consumers where it is used as room or floor heating, and to generate domestic hot water. The domestic hot water gets heated in a heat exchanger, which is a primary supply water, transfers it heat to the water coming from the tap. So we can see here, hopefully on the images, we can start to see the flow path of water come through. So the left-hand image, we can see the water coming through, heated water. As it goes through the plate, it starts to cool down, and then we're returning the cooler water back to the network. And also very similar on the other side, so on the hot water side of things, again, hot water coming in, we use the energy, so we're transferring that through the plate, and then we're returning cooler water back out. And the same on the right hand image as well. They're just different configurations of HIU. One's heating, one is hot water, and the other one is a different model of HIU. I think the important thing to remember, and one thing that we will talk about shortly, is the delta T, and that's the difference in temperature of the water that's coming into the HIU and the water that's going back out of it. So delta T is something you'll hear us talk about quite a lot. For room heating, the supply water might need to be used directly. Alternatively, a heat exchanger could also transfer the heat into internal circulation. So what we're saying there, we have direct or indirect units. So you can take the primary supply and put that straight around the tertiary circuit, around the heating circuit. But what we do tend to have there is, if there's a leak or something, the whole system can start to fall over. Whereas if we put it through a plate heat exchanger, we are keeping that mechanically separated via the heat exchanger itself. The supply water, which is now cold or lukewarm because the heat's been transferred to domestic hot water and room heating, then returns back to the district heating plant, and district heated water circulates endlessly in a closed pipe system. So we spoke before about there's been a closed loop and the water circulating around it. The key that we are looking for is to take hot water, withdraw the energy from it, and then put it back into the system cold for them to be reused as energy. The way that we record the heat use is via a heat meter. So a heat meter is a device which measures thermal energy on a supply side or return side of a heat generating or heat exchanging device by measuring the flow rate and the heat transfer fluid and the change in its temperature, so the delta T between the supply and the return legs. Typically used in industrial plants for measuring boiler output and the heat taken by a process, and for district heating system to measure the heat that's delivered. So what we take in here is the equation, the way that a heat meter works is that we take the flow temperature that comes into the HIU, we take the return temperature that goes back at the HIU along with the flow rate, and that then allows us to calculate the amount of energy that's being used. It's vitally important that we have a big delta T. So a lot of people, there's a misconception that what you want to be doing is sending hot water back to the centralized plant because you don't need to use much energy to reheat it. It's not the way. We need to withdraw as much energy as we can using the plate heat exchangers. So the bigger the delta T, with the flow rate, you're going to start to use your energy. If you're just whizzing hot water around, you're not taking any energy out of the system. So what you want to make sure we're doing is the system is balanced correctly, and we're taking the right amount of energy from the system. And the heat meter will allow billing companies to be able to take those readings and bill each individual apartment for the energy that they are using from that district heating centre. And they're generally supplied on the return leg of the HIU. So once the hot water has gone through the HIU, we then start to record what it is, so we can then start to make sure everyone's getting billed correctly. So we spoke about delta T, and the delta T is the most common use of the word in the HVAC industry, meaning the difference in the temperature difference. So in the temperature before the plate heat exchange is 75 degrees, and after is 55 degrees. That means we've got a delta of 20 degrees. Because that's the amount of energy that's been withdrawn or withdrawn by the heat exchangers for use within the system itself, the energy that's been consumed. So the bigger the delta T, then the more efficiently energy is used, with the benefits to the overall system operation. So what we're looking for on a system as a whole is we're looking for a low return temperature. We're looking for a wide delta T, because what that means is that all the heat that is being produced by the energy center, it's being used efficiently. If we just then start to circulate hot water, essentially we've got a very expensive paperweight sitting in a plant room that's not doing anything. So we want to make sure that we're drawing that energy as best we can. And there's different conversations about what we need as a delta T, but the thing to remember is we just want to be able to have a good delta T. You can feel it if you ever come to a HIU, if you run, say, for instance, the domestic hot water, you put your hand on the supply pipe, you'll be barely able to touch it, and you should be able to put your hand on the return pipe, and it will be a lot cooler. And that's because we've drawn that energy through the plate heat exchanger, and that energy has been used efficiently. The key to remember is we want a cool return temperature. Always want to make sure that return temperature is reduced as best we can. Another one we'll talk about is delta P. And the delta P is the differential pressure through the HIU. So the delta P, or pressure difference, or differential pressure, usually refers to technical words to the drop of pressure in a piping system, a heat exchanger, or another machine where liquid is passing through. The delta T symbol, which is the triangle, is a fourth letter of the Greek alphabet, and the Coptic alphabet. Delta is used as a mathematical symbol which represents the difference between two values. So what we're looking for here now, the HIU needs a certain amount of energy to work. And a HIU will have a minimum and a maximum operating bandwidth of where it can work. So for instance, we work off 35 kPa, so 0.35 of a bar, or to 165 kPa, 1.65 of a bar. And that's the differential pressure that we're looking for. Now, if we're under that, if we don't have enough energy, what tends to happen is the HIU won't perform as it should do. Often we get people call us up and say, no, I'm not getting good hot water on my HIU's not working because the hot water isn't working. And what's happening is they're turning the tap on, they're getting hot water for a very small period of time. That water then turns to go to sort of like lukewarm water, and then it dies off. And all that means is there's not enough hot energy coming into the plate, and the cold water that's coming is dominating. So what we want to make sure we've got enough energy, good energy coming into the plate to make that heat transition take place. So generally, if we've got low delta P, then what that refers to, what means to us is that we haven't got enough energy going around the system itself. The other side, the flip side, if we've got too much, we can have a noisy HIU, so the valves can start to make noises because we're forcing water through a very small orifice. So we have issues when it comes to that. And generally, we've got hot pipes all the time, so people can feel it because the valve seats have been forced open. We're trying to put too much velocity and too much hot water through the pipe itself. So it's very important that we make sure the system is designed to make sure it works in the bandwidth. And the way to do it is what we use, what we call an index point. So we want to know that the furthest HIU on our system is going to get enough energy. So if the minimum is 35 kPa and the maximum 165, if you set your furthest HIU on the system for the pumps to reach out at 50 kPa, you'll know you've got 15 kPa band or difference there to play with, but the furthest HIU is going to get enough energy. Then as you come back towards the energy center, then you're going to have enough energy coming back up without going too high, to make sure that every HIU has got the correct stuff, the correct energy going into it. Now we measure delta P by going across the flow and the return. So on the HIU itself, there's two binder point connections. This is referring to ours. Obviously, the manufacturers are slightly different. But what we do is there, we take those two caps off, we install two binder points, and what we have is like a high pressure manometer or a chondrometer, and we plug two plugs into there, and then we let the system run. And then what that'll do, that'll give us a reading of what the system is doing, and it will give us that delta P. So the difference between the flow pressure and return pressure, and it will give us that delta, so we know whether the HIU is operating within its energy levels as well. Not a lot of people carry chondrometers. There is a way you can work off the heat meter via the temperature and the flow, but predominantly we use a high pressure manometer within those binder ports to make sure that we're getting enough energy into the HIU itself, to make sure it's working as it should be. So very important. So we need a high delta T, and we have to make sure that the delta P is well within the operating conditions of what the HIU requires. Quick overview of our range. We have sort of two blunt range at the moment. We have our SAT K20 and 30 range, and the 22 and 32. So direct and indirect units. They all, one was a single plate, one's a twin plate. Very similar in the way they look, obviously, apart from the ones got the single plate. PCBs, all the technical information is on there as well, so there's all different factors on there. Some of the figures that work on it, so the SAT K20 and SAT K30 models are available as direct or indirect units with the direct domestic hot water capability of 70 kilowatts. They're an integrated PCB with electronic controls the functions of the HIU, removing the need for mechanical valves. So there is a difference, obviously, between mechanical and electronic HIUs. We have a PCB in ours which controls that, but the PCB's also got a number of different functions and setting capabilities. So we can enable prepayment. So if the customer is not necessarily on a on a tariff with an energy supplier, we can give them a prepayment option, which means they have to preload it with credit. Then that, if it's not on there, you can switch off the controls so they don't get any heating or hot water. We can have a low temperature mode, so if you want to go into underfloor heating, etc. We've got the capability to do that electronically. We've also got a preheat function, and now what the preheat function is for domestic users. So if your HIU is the furthest one away from the energy center, when you run your tap, there is a potential that it's going to take you a long time to get your hot water because you've got to draw it through the ambient losses through the system. All the preheat does is just keep the plate heat exchanger warm, so the electronic valve will just pulse open and close to make sure that the plate stays hot at any one time. We've also got a built-in diagnostics function, and this will show fault codes, which is a big benefit for us. So if people ring us up saying my HIU's not working, and we can say, okay, well, what fault code is it showing? If there's not a fault code, it's generally not the HIU. It's something to do with the system itself. So we do have a built-in diagnostics function, which we have a list of fault codes for, which we can talk through how we can repair those over the phone or send an engineer out to look at that. Heat and hot water can easily be adjusted. So we've got two potentiometers on the front, literally a case of inserting a screw, turning those up or down, so we can increase or decrease the temperatures of the heating and the hot water. And yeah, that's a very easy function we have. And there's also a series of dip switches within the HIU, which we can put in different configurations to enable or to switch off some of the functions that come with the HIU itself. SAT K22, SAT K32, it's our most advanced one. It's our new HIU on the market. It's been out for about 18 months, 2 years now. It's an evolution of the 20 and the 30. It was 5 or 6 years in development. So we've got slightly different ways of it working. We've got a higher maximum differential pressure. We've got to 600 kPa, whereas before we could only go to 165 without fitting a separate kit. So we've got we can see that looks slightly different. We've got fully insulated pipe work, etc. on those. But the SAT K32, it's our most advanced electronic functions with the latest intelligent range of HIUs. The advanced electronic features of the 22 and 32 can protect the heat network from inefficiency. And the key is that we want to protect the heat network. We want the heat network to run as efficiently as possible, so everybody gets the benefit. The unit has the ability of the maximum allowable primary return temperature to be set independently for both heating and hot water. And what we mean by that, We've spoken about getting a good return temperature to the HIU. On our SAT K32 and we can set what we want that return temperature to be. So if we want to allow the maximum to go back to the network to be 40 degrees, the unit will modulate secondary output temperature in order to produce prime return temperature of 40 degrees or lower. So we have got protection there for the network itself. So it's a very good function to make sure that the system is balanced or the network is balanced correctly, and it protects it from high delta T, so we're not just circulating hot water around there, therefore damaging the inefficiency of the system itself. To further protect the network from inefficiency and failure, the maximum primary flow rate the unit can take when in heating mode can be set by the HIU controller. Once set, this will ensure that the apartment space heating demand can never exceed the design's intended load. So if the system is designed around a certain load, we can program that into the HIU and that will then deliver that set load, so it's never going to imbalance the system itself. This protects the network from failure should cold weather, domestic hot water peak demand and multiple apartments and maximum space heating coincide. And what we're saying there, we spoke about the diversity factor, we spoke about that demand, but if there is a large demand, we can set the HIUs to never exceed a certain amount, so we're not starving one HIU over the other. We can share that load across the HIUs itself. The conventional HIUs provide a secondary heating system with water set at a temperature and relies on a thermostatic radiator valves within the space heating to modulate the flow through the emitters and to maintain the desired room temperature. So if radiator has not been balanced, then the higher than the required flow rate results in higher return temperatures and the design calculations, especially at low heat demand. So we have some very clever functions within the HIU itself, which allow us to protect the network. It's all about future proofing as well. At the moment, I say we are where we are with third generation heat networks. That's obviously going to change as time moves forward. If we've got a future proof product in the marketplace where we can just electronically change those settings, it's always going to set us in a good position for the installers and for the people using the units. That it's just a case of changing a parameter as opposed to actually swapping over the HIU itself. So we spoke about RTL, about the return temperature limitation. This will always keep there. So even the department approaches the required temperature, the HIU will ensure that the prime return remains as low as the set point temperature. And another new feature of this HIU is the way that the HIU is controlled. So we have an integral room control allows the tenant to set the preheat on or off, or program the preheat in a similar way to program its heating. So what we mean by that, preheat generally is either on or off. It's like a trickle bypass on some units. So we just keep a very small bypass open and we start to circulate hot water through the plate. Now, obviously there's a cost to the end user there because they're using energy, and it could, traditional units are either on or off. Now, what we have on this one is we have a presettable preheat, and what that means, you can set it very similar to you would your heating or hot water. So if you know you're going to want hot water at 6:30 in the morning when you get up for a shower, you set your preheat to come on at 6 o'clock. You've only got 30 minutes then of it heating up, and you're not paying for 24-hour cycle. So you can sort of set that to your own preferences and your own demands. It enables the network to more efficiently, because if you do have a preheat on, we're still going to start sending higher temperatures back down the return pipe. And it just becomes more cost effective for the end user. And it says there, the tenants are not paying for preheat when he doesn't need it. He only use it when he needs a benefit. So it's a benefit for the network, but it's a benefit for the end user as well, because you're not paying for that 24-hour trickle bypass or wherever it may, the preheats may work. You can set it as and when you want it to function. So it's a good, it's a good feature to have. Some of the literature that we have available, so we have lots of IOMs, data sheets, heat interface guides, heat network guides, design guides for heat networks. We have all this information available across all of our ranges. We have, more than the SAT K22, 20 and 30 and the 32 and 22. We have a whole range of heat interfaces for different installations itself. IOM instructions of how to fit heat meters or differential pressure DPCVs, but also the room controllers as well. So we have a lot of information that accompanies the heat networks and the HIUs itself. And that's it for me. I apologise for the issues that we had at the start of the presentation with everyone not being able to see it. So yeah, I do apologise for that. Helen, I'm not sure whether there's any questions come through, with anything that anybody has fired through.
Yeah, thanks for that, Ed. We do have a question from Patrick Mann. He asked, can you apply the HIU units to any district heating system or fuel source, such as biomass?
Yeah, I mean, the fuel source to the district heat network is irrelevant. What we're trying to do is generate heat to generate hot water, and that then is stored in a clarifier. So if a biomass is producing heat, then absolutely you can then use that to heat the water to go into the district heating. So there's no there's no restriction on how you heat the water. Obviously, the more energy efficient you can do it, the better. But yeah, if you have a biomass system, then you can do that, and then the HIU can be put onto that network. As long as you've got the correct pumping, correct size pumps, etc., to circulate the water around. So yeah, the actual production of heat isn't an issue as long as we can generate enough heat for it to work. So yeah, you can do that.
And then there was one more question about basically the differences between mechanical and electrical HIUs. Why would somebody choose an electronic HIU?
Okay. Again, we're talking about future proofing now. So obviously, as time moves on, society moves on, and the way that we work, I think, is very different now. Electronic HIUs with a Visor Modbus and all the different ways we can connect them now, a lot of this work can be done remotely. So we talk about the way that heat generation is working, we talk about the different kinds of heat networks and the way that they operate, whether we go to low temperature heat networks, whether we stay as we are, whether, again, the fuel source changes, all this sort of stuff. As buildings develop, they change as well. There might be an extension to a building, which means parameters have got to change. Now, mechanical HIU, which might work off, say, for instance, standard thermostatic mixing valve, someone's going to have to go and start to manually work on all these units, whereas an electronic unit itself can be dialed into from remotely. We can look at all those settings, and it's a very simple process of changing those parameters. And again, we're talking about evolution, not revolution. Again, there are some very, very good mechanical units on the market. I'm not slating mechanical units far from it. I'm just saying that when we future-proof, when we start to move forward, when people want these automated buildings now, electronic HIUs are going to allow us to be able to dial into them, to change their settings remotely to suit whatever is going on in the building at any one time. So that's just the main thing. It's all about future-proofing and see how we go moving forward, I think, with the way buildings are occupied and the way that they work.
Great. And then there's just one last question, Ed. Are you able to link a HIU to an invented cylinder?
Well, you've got to remember, what we've got to try and do here is we have to try and generate. We've got to generate pressure. So we have what's called a ProSol unit. So if someone wants to store hot water, we can connect a HIU directly to a cylinder, and we can take the hot water production from the HIU and put it into a cylinder, essentially. So you can connect them, and we do it on the market. I said there is one called a ProSol unit. But we're trying to come away from the world of stored water to a degree. There's still actually absolutely a marketplace for stored water. But what we're looking at here is instantaneous production of heating and hot water. But we do have a unit, like I say, called a ProSol, which sits on top of a cylinder, and that's where we put the stored water into it as well. So we do have that option as well, yeah.
Great, and that's all the questions wrapped up. So unless there's any more.
Thank you. No,
okay. Nothing else coming in.
No, okay. Well, thank you, everybody. I hope you found it beneficial. I do apologise for the issues that we had at the start. I wasn't aware that you couldn't see my presentation, so I do apologise for that. And yeah, keep your eyes peeled for some more of our webinars moving forward. So thank you all for your time.